talk about fluid dynamics. Though we talk about various phenomena like these are the things happening and so on, we learned something like how to represent those particular flow configuration in terms of mass we have learned, but we never solved actual fluid mechanics problems. To solve such kind of fluid mechanics problems, maybe using pen, paper, or even on computers and so on, we require certain principles, what we will call as conservation principles. So let me write it down. The first one is conservation of mass. The second principle is conservation of momentum, especially which is called conservation of linear momentum. The third one is conservation of angular momentum. And the fourth one called conservation of energy. Conservation of energy. And there is one more powerful law, which is called conservation, but is basically people call it in terms of entropy principles. So we are not really saying conservation, but we just say it something like entropy principle. So these are the 5 principles we require it for any kind of flow configuration. What I mean for any kind of flow configuration is basically you might be having a fan. It can be even wind turbine blades. Is rotating and flow might be coming, going out. It can be that. It can be something like you have an aeroplane. And there might be something like gas turbine blades and exhaust is coming out, going out. Maybe within the system or exterior. Exterior in the sense over the aeroplane, or interior where combustion is happening and so on, so kind of stuff. Or it can be even on your motorbike. Where combustion really happens in that IC engines and exhaust gases coming out and flow passed over that, flow within internally. You take any problem, it always connected with conservation of mass, conservation of linear momentum, conservation of angular momentum, conservation of energy, and entropy principles. Based on that, these things really work. And especially the first one called conservation of mass. For example, if I am taking, there's a wave breaking phenomena. This is the sea. Let us assume. I pick very tiny element somewhere within the fluid on Eulerian coordinates. That means I fix my x-axis, y-axis, and z-axis. Over the time, I'm going to really track only this particular object. Track in the sense only in terms of time. I'm going to visualize within that certain domain where I'm going to freeze, continuously observing same x, y, z information. I don't travel with that. However, fluid might really come into picture. It might go out of the system. If I am going to zoom that, maybe the object looks like this one. In that, this is arbitrary volume. When I am focusing on that kind of particular arbitrary volume, usually we call that name as control volume. Control volume under observation. And this control volume can be as large as possible, as small as possible. It's up to the observer. For example, the same control volume, one can also even construct something like such a big control volume also one can really construct it, where on one side air is there, on the other side you have liquid. How much flow really comes in terms of liquid, how much flow really goes out in terms of air, also a control volume. Now, if I really look at such kind of control volume, maybe for example, your control volume for fighter aircraft, maybe you can always focus only on the gas turbine blade, or your objective is the exterior flow happening over the aeroplane. Then that means your control volume may be your entire aeroplane. Maybe your control volume might be complete wind turbine blade. The whole point of this control volume analysis is you will apply conservation principle like mass, momentum, energy, maybe entropy principle on those things. Try to understand what might be the input condition, what might be the output. How much flow, atmospheric flow is far away, 10 kilometers away from the wind turbine. And as it is approaching this wind turbine blade, how it is getting modified. And as it leaves the wind turbine blade, how it is further going to develop instabilities and so on. So to handle all these kind of systems, we require something like a volume under observation. Once you fix that volume, you will be in a position to really apply these principles to tackle what is coming in, what is going out. More like a budget you are trying to do. You have something like a bank account, how much money is coming, when it is coming, how much it is going out, and so on, so kind of thing. You require certain kind of account to track it. In the similar way, here for fluid mechanics problems, heat and mass transfer problems, or boiling, condensation kind of phenomena, or perhaps even fluid with electromagnetic kind of things, you require a sophisticated mathematical volume known as control volume. So on Eulerian coordinates, you stand it at one location, you fix something like control volume, try to observe what is happening. So if I am zooming in one of the particular coordinates, maybe if I fix the coordinate axis, something like y-axis, this is x-axis, and let us call this is z-axis. Origin can be anywhere. Maybe origin might be here. So with respect to that coordinate system, I'm going to talk about something named this entire plane is at x location, and this entire plane is at x plus dx location. To color it, what I'm going to do, use this. So the surfaces, what I'm trying to show by color, are at those x and x plus delta x locations. This entire surface at x plus delta x. Similarly, that backward surface is at x location. Now let us look at y planes. Y plane perhaps at y plus delta y locations. So this plane is at y plus delta y location. And the bottom plane is at y location. The entire bottom one. This is at y location. The backside surface, possibly green color. Let us fill it by green. and the frontal one also green. So such kind of surfaces. The back one is Z plus Z location, and forward one is, forward means this surface is Z plus delta Z. This is the first coordinate system what we are trying to follow. Any component trying to move velocity component in the x direction, we associate with variable u. Any component which is in the y direction, we will associate with v. Any fluid velocity component, Eulerian things, associated with the z1, we call it W. Now the budget, what we are trying to do, control volume. In that, we are trying to look at mass conservation principle. How much mass enters and leaves from x direction? Similarly, how much it enters in the y direction and how much enters in the z direction. These are the things separately we are going to track it. When we are going to track this entire thing, in case what is coming in, what is leaving out, what is coming in, what is leaving out, and so on, this entire summation, if I am going to look at, perhaps if there is an imbalance in between what is coming in, what is leaving, maybe mass might be accumulating within that box or mass might be annihilated within that box. Any imbalance in terms of mass coming in, mass leaving out, supposed to be connected with something happening with mass within that control volume. This is the analysis what we do. That means fluid might come in x direction, but nothing leaves in the x direction, nothing leaves in the z direction. Maybe fluid might be leaving in the y direction. This might be happening. For example, if you are taking your overhead tank, this is the overhead tank where you are storing a lot of water and pipeline really comes down. There will be some walls, check posts and so on, so kind of thing. Finally, you will have something like a tap. In case if mass is coming out of this thing, maybe it might be moving within this control volume here. If I am going to show within that control volume, maybe fluid might be entering, fluid might be leaving there. Maybe if I am going to pick my control volume up to this part, fluid might be coming in this direction, fluid might be leaving in that direction. Any imbalance means something is happening within the system. Maybe you completely locked it, closed it. Fluid is not actually going out. So no fluid is coming down, no fluid is going out. That kind of mass conservation, what we are trying to do. Okay. Now let us carefully do math in terms of estimating it. So what I would like to do is mass coming in x plus mass coming in y direction plus mass coming in z direction. This entire mass minus whatever the mass going out from x plus delta x, similarly going out from y plus delta y, similarly going out from z plus delta z. This entire stuff supposed to be within that control volume, how mass is getting accumulated. So del by del T, the variation happening in terms of mass, which is density, multiplied by the volume delta X, delta Y, delta Z. Because plane is at X location, X plus delta X, Y plus delta Y, Z plus delta Z means this entire thing, this is delta X. And Y direction, this is delta Y, the volume. And this one is delta Z. So the total volume of the present system is delta X, delta Y, delta Z. Density multiplied by volume is mass. So within that, whether you have air, whether you have fuel, whether you have combustible gases, or whether you have just saline water, it doesn't matter. Whatever that total mass of that particular fluid within that box, how it is going to increase over the time if something like mass coming in X direction minus mass going out from X plus delta X, Y plus delta Y, Z plus delta Z. Now the question, the sign we have to really decide. Maybe coming in is more than going out. Naturally, this is supposed to be plus. Density is by definition positive definite. Volume is also delta X, delta Y, delta Z is positive definite. So del by del T variation over the time, gradually that mass within that box is going to increase. Volume might not be increasing. In that case, density may have to increase. It might be compressing. More and more mass really come and squeezes into that box. Think of something like there is a classroom. People are coming and there is something like exit. More number of persons are coming, entering into that box or in that room, but not going out. Naturally, they will be jam-packed. More amount of mass accumulated inside the system. But compared to the number of people are coming into the system, the number of people going out are more. Then naturally, even though the room already have a lot of people, gradually it will deplete. That is the thing what our mass conservation principle tells us. The same thing what we are trying to do in mathematical terms, how to really represent that. So mass coming in. So how I am going to really do mass coming into the system? Density rho, the velocity u, at which location it is coming in at X location. From which area it is coming in? From X area. That means each and every location on that surface having a velocity u at a given X location, but it will be varying maybe in the Y directions, Z direction. So from this surface, there are so many holes or so many kind of places through which mass can really enter into the system. At each location, it has a density rho, it has a velocity u, and integrate throughout that surface. The throughout that surface is this length multiplied by this length. That means delta Z multiplied by delta Y. This is the mass coming in to this system. Similarly, what is the mass coming into Y direction? Rho V calculated at Y multiplied by delta X, delta Z. Let us look at. In the Y direction, the fluid comes with a velocity V multiplied by delta X multiplied by delta Z. That is the mass what is entering in. Similarly, the mass which enters at Z direction is rho V Z delta X multiplied by delta Y. Let us look back. So Z direction is from the backward direction. Some fluid is coming into the system at each and every location. So rho multiplied by velocity with which it is coming in and from which area it is coming into the system. That is your delta x, delta y. Now let us look at the units. Units kg per meter cube. Velocity is meter per second multiplied by meter, meter square. So meter cube goes, it is kg per second. This is the mass entering per second per unit time. This much amount of mass is coming in. Now let us estimate what is the mass going out of the system. Minus rho in the x direction, velocity u calculated at x plus delta x multiplied by delta y, delta z. This analysis, what we are doing, we are trying to pretend that the entire box, arbitrary box, what we have assumed is a cubical box. That is the reason I am in a position to write. But this can be generic, and we will see that generic way of writing it later. Rho v entering at y plus delta y multiplied by delta x, delta z. From that plane, this much amount of mass is going out. Similarly, rho, I'm sorry, here it's not v, it's W. Rho W calculated at z plus delta z multiplied by delta x, delta y. This is the mass going out. Again, units, rho kg per meter cube multiplied by meter per second multiplied by meter square, so kg per second. Within that control volume, how the rate of change because of something entering in minus something leaving out, there must be some change happens. It might be finite quantity, it might be zero also. Del by del t. Why del by del t? Because we fix the volume. We are not tracking individual fluid particles. Maybe the individual fluid particles might be coming in. This one enters, maybe some other one leaves. So we are not tracking individual particles, but at a fixed location, Eulerian coordinate system. Del by del t of rho delta x, delta y, delta z. Units are kg per meter cube multiplied by meter cube per second, kg per second. Now use Taylor series expansion. So u at x plus delta x, u estimated at x plus delta x location is u estimated at x location plus delta x multiplied by del u by del x estimated at x plus delta x square by 2 factorial multiplied by del square u by del x square plus and so on so terms. So typically we write it this one as u estimated at x plus delta x multiplied by del u by del x plus order delta x square. Any factors or higher order terms, we write it in terms of this big O notation order delta x square. Similarly, u calculated at y plus delta y can be written as u calculated at y location plus delta y multiplied by del u by del x plus order, I'm sorry, this is delta y order delta y square. This is the way we write it. Now, velocity components, if I would like to really write it, the velocity v at y plus delta y is v calculated at y plus delta y multiplied by del v by del y plus order delta y square. Similarly, W calculated at z plus delta z. Can you help me out? Is equal to? Hello?
W at z plus
calculated delta z multiplied by delta z del w by del z plus order delta z square. This is the way we have to expand. Now we have at x locations x plus delta x location y, y plus delta y, z, z plus delta z. So simplify that. So rho u calculated at x delta y delta z minus rho u calculated at x multiplied by delta y delta z plus delta x del u by del x multiplied by del y del z plus higher order terms. Okay. Similarly, the other term rho v calculated at y delta x delta z minus rho v calculated at y delta z plus delta y multiplied by del v by del y delta y. What is that? Delta x delta z. So delta x delta z. The third component is rho w z delta x delta y minus rho calculated at w at z location delta x delta y plus delta z multiplied by del w by del z multiplied by delta x delta y. This entire thing supposed to equal to del by del t of rho delta x delta y delta z. Now simplify it. Taylor's expansion. Let me cancel out terms. This term gone. Similarly, this term gone. Similarly, this term gone. So the leftover terms are at least at order delta x square limit del u by del x delta x delta y delta z minus del v by del y delta x delta y delta z with rho term always be there. Here rho is there, here also rho is there, here also rho is there. Rho minus rho w by del z delta x delta y delta z is equal to del by del t of rho delta x delta y delta z. Is that fine?
Sir.
Yes, sir.
Sir, why are we assuming the density field rho to be the same at x and x plus delta x? Won't that vary too specially?
That can also vary. So if I would like to really consider that, something like at entrance, you have one kind of density of fluid particles coming in, exists some other kind of fluid particles are going out. I have to even bring that also into the picture. But at this point, what we are trying to do is simplifying it like, I'm not worried about in terms of densities, but something like fluid is coming in, fluid is going out and so on, so kind of thing. Then what will happen? Then I will generalize it when our density is also changing. The same analysis where I am trying to expand in terms of use, but I need to expand it in terms of rho u terms. So rho u estimated at x, rho u estimated at x plus delta x. That is the way we will go ahead. Okay. Hello.
Yes, sir.
Wonderful. Once this picture is clear, that generalized picture, we will come back. So now ask a question when limit delta x multiplied by delta y multiplied by delta z tends to 0. Why we are looking is infinitesimal quantities, if I am going to look at, or more proper word is, if we are going to look at something named differential analysis. Anything in terms of differential equations, if we are going to really look at it, writing calculus of things, the natural question to ask is this delta x, delta y, delta z, if it is independent of that, that means whether it is very big volume, whether it is very small volume, whatever might be the things, I can always track all that volume by infinitesimal elements. Then naturally on both sides, delta x, delta y, delta z really comes out of the system. And this delta x, delta y, delta z are independent of which location you are going to look at, because you are the person who is going to fix my x location is this, my x plus delta x location is this, my y location is this, my y plus delta y location is this, my z is this, my z plus delta z location is this, and this delta z, delta x, delta y, nothing to deal with fluid particle positions. It is based on the observer. You lock the frame within these volumes. What is happening? I would like to really understand. Because of that, I can really pose the limit. Limit delta x, delta y, delta z is very tiny volume. Then I can really write a differential equation. It's not necessary that I have to pose such kind of limit. If I pose such kind of limit, then we will call that kind of analysis as differential analysis. If I don't pose that kind of thing, but still keep the volumes, then we will call integral approach. We will see that. We will come back for that integral approach. But at this differential level, if I am going to really look at this limit, then naturally what I am going to end up is del rho by del t is equal to minus rho del u by del x minus rho del v by del y minus rho del w by del z we are ending up with. Now the question really comes. The mass what it is entering, you always counted only in terms of u, v, w raja. These are velocities. But actually for me mass means from that surface, how much rho, how much velocity, how much area. The area for this is delta y, delta z. So when you are going to fix as an observer delta y, delta z, my mass is always be function of x. That means my entire rho u is function of x. In that case, what I am supposed to do is expand this entire thing in terms of rho u's, rho v's, rho w's. Expand together completely. If I am going to do the same analysis happens, calculate rho u at x plus delta x is rho u at x multiplied by delta x and replace this u by rho multiplied by u delta x square by 2 del square u by del x square supposed to vary in terms of rho u component. Rho u calculated at x. This u component changes to rho u and delta x square components. Rho comes here. Rho u calculated at y plus delta y. And u also changes to rho multiplied by v. Similarly, rho v. Here u. I'm sorry. This is u. Here u. rho V, complete expansion, and here V also becomes rho V, and here rho W, and this one changes to rho multiplied by W. This is the complete mass balance, even in case your density is going to change as a function of x, y, z and t. If that is the case, then naturally what we are going to end up here, rho u, this one ending up as rho v, and this one ending up as rho w. And that means we have an expression in terms of del by del x of rho u, and here we have expansion in terms of del by del y of rho v, generic one. This one we will have expansion as del by del z of rho w, and rest of the things same. That means my entire expression turns out to be del by del x of rho u plus del by del y of rho v plus del by del z of rho w with minus sign. Minus this, if we are going to write it in a general way, del rho by del t per unit volumes, because we have divided the delta x, delta y, del z on both sides. That means we have taken out volume common out of the system. So kg per second turns out to be kg per meter cube per second, which kg is a density multiplied by volume. So volume goes off. So density per second we will be ending up with. So del by del x of rho u plus del by del y of rho v. Here it's not y, it is v, plus del by del z of rho w is equal to 0. In shorthand notation, if we are going to write del rho by del t plus divergence or gradient acting on complete rho u component is equal to 0. This is also written as in shorthand del t rho plus del dot rho u is equal to 0. Maybe if I would like to write it in terms of my initial notation, it will be my same del t plus del of rho u inner product we have to really look at. So it can be any component, something like I. So I by del xi is equal to 0. This entire thing what we call as conservation of mass. Conservation of mass. Fine. Now there will be many corollaries kind of things. In case my density, first question, in case my density of that flow rho is not a function of x, y, z and t. this is not a function of xyzt, but it is just a constant value. That means some fluid in a box or in a room, fluid is coming in, fluid is going out. Within this entire box, wherever I measure, I will be having the same density. In case if it happens, such kind of systems, this entire conservation of mass, del rho by del t plus your del rho u by del x plus del rho u by del y plus del rho w by del z is independent of this time. So this term is gone. Rho is independent of it, so it can be really brought out. Rho is independent of xyz coordinates, it can be brought out. Rho is independent of xyz, it can be brought out. That means del u by del x plus del v by del y plus del w by del z multiplied by constant is equal to 0. This happens to the system. So though you begin with mass conservation principle, what you are ending up with is del dot u is equal to 0 as long as on the Eulerian frame you see your density constant throughout the system. This is one. Is this point clear to everyone? Hello?
Yes, sir.
And this also called continuity equation. Now let us look at second case. Hey Raja, within that box, I really have no idea whether density is constant or not. I don't know. But what I can assure you is whatever might be the fluid particle really comes into the system, whatever the same fluid particle really goes out. Think of a situation, fluid particle density is constant throughout its motion. What I mean, it's not necessary that same fluid might be going, but think of a situation, air particles is more like your oceanic kind of things. Air particle is coming in and also liquid particle is going out. There might be some aerosols are also coming in, going out, and so on. But whatever these things, combinations, they are coming in, going out within this entire control volume. Different materials are coming in, going out, and they have mixed up also. But any individual fluid particle you take it, throughout its journey within that box, its density is constant. Is that clear? What I mean? It might be mud, clay, many kind of mixture, combustible products, all these kind of combinations are entering, going out of the system. But its density is not varying for any particular fluid particle. Or whatever the fluid particle under consideration, its density is not changing. In that case, Lagrangian term d rho by dt is equal to 0. This we have to use. If that happens, we already know d rho by dt is del rho by del t plus u dot del rho is equal to 0. U del rho by del x plus v del rho by del y w del, we have derived that. The connection between Lagrangian and temporal and spatial terms we already know. This is the shorthand notation. If this one becomes 0 and my mass conservation principle says that del rho by del t plus divergence of rho u is equal to 0. This is from mass conservation. This term. This one, individual fluid particle density is 0. such kind of systems what we call incompressible system. Now we are looking at another case named incompressible systems. That means the individual fluid particle density is equal to 0. The variation, what I mean. And we know how to connect Lagrangian with Eulerian. That means begin with your mass conservation principle. This means del rho by del T plus divergence of rho u. The way how I can really split rho multiplied by divergence of u plus u multiplied by gradient of rho. This is also 0 by product rule. You can check it even by initial notation. This is the thing what you will end up. So by mass conservation, we got this one. If I pretend that it is incompressible, then del rho by del T plus u dot del rho is equal to 0. That means from both the equation, what we will end up is this entire term, are same. That means rho multiplied by del dot u is equal to 0. We will end up with. This means again we will end up with del dot u is equal to 0 as the mass conservation principle for an incompressible system. So two limits we try to really look at. In case I pretend within that volume the density is constant, we will end up with del dot u is equal to 0. It is nothing to deal with incompressibility assumption. It is just to say that your density is constant everywhere. If that is the case, it turns out to be del dot u is equal to 0. Similarly, if I go begin with incompressibility assumption, again I will end up with del dot u is equal to 0 because of mass conservation principle. And this is a powerful statement for solving equations using computers, try to get red, blue, green kind of pictures. Basically, most of fluid mechanics problems, we will try to handle this del dot u is equal to 0 as mass conservation principle, though the original mass conservation principle is this one. By bringing certain assumptions. That is the story of our mass conservation. Tomorrow's class, we will look at momentum conservation. Once we have that idea about that, I will introduce something named Reynolds transport theorem. And once that Reynolds transport theorem is well understood, we work out examples to appreciate how to handle fluid just coming in, balls are moving here and there, and perhaps how rockets are accelerating and so on. So kind of practical examples. But that minimum math up to momentum equation is very essential to handle interesting problems. Without math, we cannot do. We can do science in a very better way, excellent way, if we can pick this tool named maths.